Hi, I am Professor Alexis Fenate, and we will answer this question. The determination of dynamic pseudo-equilibrium moisture content can significantly affect the accuracy of high industrial dry design calculations. Many materials of biological origin require precise conditions for drying, and for the most part, moderate conditions. Since the dynamic pseudo-equilibrium moisture content increases with decreasing drying gas temperature, failure to consider it will result in unavoidable design errors. This is especially critical for concurrent dryers with high residence times, which typically have low outlet drying gas temperatures. I will explain this answer in detail below. The unit for expressing moisture in drying kinetic studies is the moisture ratio, which can be defined as the moisture content not removed in relative terms. It's given by the ratio between the mass of water present in a material at a given time and the total mass of water that can be removed by drying. It's understood that, at the beginning of drying, the moisture ratio is equal to 1 and decreases with time. This way of expressing moisture was established by Warren Lewis in 1921 and is still widely used today. The drying kinetics of a material, on the other hand, refers to the behavior of moisture decrease during drying. Drying kinetics, after being fitted to a mathematical model, is the main basis for rigorous design and simulation of industrial dryers. The problem with the Lewis moisture ratio, which we will call theoretical, is that it assumes that the behavior of moisture during drying is monotonic until the moisture equilibrium is reached. Moisture equilibrium is the condition where a material has no change in its moisture content and begins at the equilibrium moisture content, which, once reached, does not change over time. In 2016, after studying the drying of 12 different materials, my research team published a series of results that refute the use of the theoretical moisture ratio for the simulation and design of dryers. In that study, it became clear that, between the kinetic stage and the moisture equilibrium, there is a transition stage, with an intermediate behavior between the two mentioned stages. In this transition step, the material continues to lose water, but at an extremely slow rate. This stage can be considered as an equilibrium stage when it is visualized within a short period of time. We term the beginning of this transition stage as the dynamic pseudo-equilibrium moisture content. This moisture content changes with the drying conditions, and it is higher than the equilibrium moisture content. It's also lower than the moisture content normally used for storage, about 10% on a wet basis, for moderate to high temperatures. However, it can be higher than the storage moisture content at moderate to low temperatures. Substituting the equilibrium moisture content for the dynamic pseudo-equilibrium moisture content in the moisture ratio equation, we obtain the practical moisture ratio, which is the appropriate expression for simulation and rigorous design of high industrial dryers. This is because the practical moisture ratio contains the actual kinetic limit. Hi, I am Professor Alexis Fanate, and I will be answered this question. In mathematical terms, the moisture ratio is given by a ratio of moisture content differences on a dry basis. The practical moisture ratio comprises the ratio of the difference of the moisture content at time t, minus the dynamic pseudo-equilibrium moisture content between the difference of the initial moisture content minus the dynamic pseudo-equilibrium moisture content. To calculate the theoretical moisture ratio, the dynamic pseudo-equilibrium moisture is replaced by the equilibrium moisture. Both start at 1 for t equals 0 and decrease with time. Although both expressions are correct, depending on the intended use, the theoretical moisture ratio is useless for generating models suitable for design of industrial dryers. This is the reason why basic research in drying, which generates kinetic models, has historically been disconnected from the applied research, which generates simulation models. The drying process is divided into three stages: the kinetic stage, followed by the intermediate stage of dynamic pseudo-equilibrium, ending with the equilibrium stage. The theoretical moisture ratio does not contemplate the existence of the intermediate stage, which is why the models generated with this assumption are susceptible to predict erroneous moisture content and the outlet of the material from the dryer when performing a simulation. Since industrial dryers are designed to work within the kinetic stage of drying, it is vital importance to delimit the model of its real limit, especially because these models are empirical. On the other hand, it's not cost-effective to design an industrial-scale dryer to dry bulk materials to equilibrium moisture, since its dimension will be unreasonable. In conclusion, modeling the drying kinetics with a practical moisture ratio implies the possibility of directly using the generated model in the simulation and rigorous design of industrial dryers. Hi, I am Professor Alexis Fanate, and I will be answered this question. The case of industrial dryers is an atypical case of industrial separation equipment design. One would expect an industrial dryer to be designed for a particular application by simulation, and then move to the rigorous design and construction stages, as is the case of distillation towers, absorption towers, etc. However, the generation of design bases and simulation models for dryers has historically lagged behind equipment construction. Distillation and absorption towers had graphical design methods prior to the advent of commercial simulators, early enough to support the construction of large refineries and petrochemical complexes. In the case of dryers, only rotary dryers had a graphical design method that has only recently been replaced by simulation models. In fact, it was not until 2016 that the company Aspen released version 9 of its process simulation software, managing to offer simulation modules for industrial dryers 34 years after releasing the first version of the program. The above-mentioned implies that the scaling off of industrial dryers has been governed basically by empiricism. This is demonstrated by the fact that the companies that build industrial dryers only take into account the amount of water to evaporate from the material to be dried in order to sell such equipment. The process followed by manufacturers is based on building dryers of different sizes. keeping certain proportions, and depending on the performance, generating black box design models, which are highly empirical and therefore highly limited. It's understood that when purchasing an industrial dryer, the company that buys it must optimize the drying conditions, marked by the plant's installed capacity. It is also understood that there is a current worldwide industrial park of dryers that were not precisely designed for the application for which they were installed. This facilitates the use of simulation models for process optimization, which must be highly accurate to meet the objective of minimizing costs and increasing profits. Since the dryers are designed to work within the kinetic stage of drying, limiting that limiting the kinetic model to its actual limit could make the simulation model more accurate, increasing its predictive capability.